as I said, I was trying to show you how non-reinforced concrete beam would behave. So in the slide, you see there is a beam simply supported. It has a span of L. We have a point load acting in the middle. So when this happens, for sure, if your force is equal to zero, the moment is equal to zero, and the stresses are equal to zero. However, once you start adding more force, so this will develop like more bending moment in your beam. And when the bending moment increases, what happens is the stress in the beam will increase. You guys remember, I think that's what we covered last class. Also, we said, okay, you know what? If the beam is affected by a bending moment, so what happens here is anything above the neutral axis will be in compression, and anything below the neutral axis will be in tension. And the stress distribution or the stress diagram is what you see on the right side. So this is the stress distribution or stress diagram, and this is the beam section over there. So you can see here there are some line with different colors, starting from the cyan, and then followed by the green, and then finally the red. And what are those three colors? Those they correspond to different bending moment. So the cyan is the least bending moment, the green is a higher bending moment, and then finally the red is the last bending moment where your beam is going to fail. You guys know that concrete is fantastic in compression and then not as great as in tension. And that's why the failure with control by the following. If the stress at the very bottom fibers become equal to the modulus of rupture, and you guys remember what is modulus of rupture, which we call it F sub R, is simply the tensile strength of your concrete, which is connected and related to the FC dash. We know that. So guys, here, this is simply a kind of a derivation to show you how can we predict the capacity of non-reinforced concrete beam. Here we go. So we know that the stress is equal to the moment divided by the, the bending moment is divided by the moment of inertia, and then multiplied by y, where y is the height of the beam from the neutral axis, the height of the fiber from the neutral axis. Then we know that the highest stress is where y is maximum. Where y is maximum is at extreme fibers. Simply the y is equal to h over 2. So this, you will have the highest stress. Then if we apply a force in the middle of the beam, the moment is related to the force and the span through this equation here. Okay, the moment is equal to the force multiplied by the span divided by 4. This is given that the force is acting in the middle. And then the moment of inertia, or the second moment of area, you guys study this in strength of material, is connected to the dimension of the cross section. So it's equal to the width of the beam multiplied by the height of the beam cube divided by 12. And the units are in millimeter to the power 4. Now, as I said, when the beam cracks, simply when the stress at the bottom fiber becomes modulus of rupture. And look at this equation here. We know that the modulus of rupture is connected to the compressive strength using this equation from the code. 0.6 times lambda times square root of FC dash. And you guys know for normal density, the lambda is equal to 1. Okay? So finally, based on the above, we can find what is the M sub CR. And what is M sub CR? The name is here cracking moment. It is the moment when the beam has this moment, then your non-reinforced concrete beam will simply fail because the stress at the bottom fiber will be equal to F sub R, modulus of rupture. Now, I know things are very dry, and that's why I always try to make things in numbers, so it's kind of better to understand. So here is my beam one more time, and the span is 6 meters, and the width of the beam is 200. The height of the beam is 600, and it is made out of concrete of 25 MPa. The FC dash is over there. So what's the question? The question is, find the force F. Okay, find the force F that will fail this non-reinforced concrete beam. So what you have to do is, number one, you have to find the moment of inertia, which is the width of the beam times the height cube divided by 12. So here we go. Here is the moment of inertia of your beam. Number two, you need to find what is your modulus of rupture, which is connected to your concrete compressive strength, where lambda is equal to 1. Very simple. So if you have concrete in compression takes 25, in tension will take only 3 MPa or 3 Newton per millimeter square. Then finally use the formula, and then you say my M sub CR, which is cracking moment. You just have to use this formula over there. It is the stress multiplied by the stress multiplied by the moment of inertia, and then finally divide by your H over 2, which is 300. Then the moment is 36 times 10 to the power 6 Newton millimeter. Remember, in general, when we talk about moment, the norm is we say the moment in kilo Newton meter, not in Newton millimeter. It's very simple. You just have to divide by 10 to the power 6. Then the moment that will cause this beam to fail is equal to 36 kilo Newton meter. Now, if that's the moment is going to make this beam like fails, then how much is the force? There is a relationship between the force and the moment. Then we can simply figure out what is the cracking force that will simply fail this beam. And to be honest, I would like to read this backwards. So now we know the answer, but let's read it backwards. So based on my math here, I found out that my force that's going to crack my beam is equal to 24 kilonewton. Okay, so what happens? So it means if my force equals to 24 kilonewton, then my moment is going to be 36 kilonewton meter, because it's FL divided by 4. So you get here your moment. And if you have this moment, guess what? The stress will be equal to 3. And because the stress will equal to 3, what happens? It means my beam will fail, because 3 is the modulus of rupture, which means concrete cannot take this much. Maximum is 3. If you get a little bit than 3, then your concrete will crack in tension. Guys, any questions so far? Are you following? I need to hear some noise, please.
No questions yet.
Okay, thank you, sir. Okay, so guys, again, I would like you to read this backwards. I'm asking you for a force that cracks your beam. And remember, this beam doesn't have any reinforcement. It is a plain concrete. It means no reinforcement. It means when these fibers here, the stress is equal to 3 MPa, then your beam will fall to the ground. Okay, so read it again one more time backwards. If my force is equal to 24 kilonewton, and because my beam is simply supported, and this 24 in the middle, and the span is equal to 6, so the moment will be 36 kilonewton meter. And if my moment is equal to 36, then this will produce here a stress at the bottom fiber is equal to 3. And because 3 is your ultimate, is your limit for the tension, because that's the modulus of rupture, then your beam is going to collapse and fail. Okay, that's it. Okay, now, guys, see what happens. I'm asking you guys, what is the stress when your beam fails? What is the stress here? Anybody to tell me? I'm asking you at this moment, that the moment that you see right now, when the stress at the bottom fiber is equal to 3 MPa, that's in tension. I'm asking you, how much in compression? Any help?
25.
Who said that?
Nicholas.
Nicholas, it's not correct. Anybody else? I'm sorry for that. Anybody else has another input? What I'm saying here, guys, at this moment of time, when your force is 24 and your moment is equal to 36, and the stress at the bottom fiber is equal to 3 MPa, what is the stress at the top fiber in compression?
Is it also 3?
Thank you, Jelly. I will give you a couple of marks for that. Thank you.
Thank
Okay,
you.
yeah, it's true. That's true. Like, yes, it is 3. Okay. So I want you guys to feel it. You know what? If concrete can take to 25, as Nicholas said, it can take up to 25. And my whole beam is feeling while the stress is still only 3. Is that the best thing to do? It means I'm wasting my material. So what happens is I'm going to take you from this, and that's exactly the idea behind reinforced concrete. If we build our beam out of plain concrete without any reinforcement, so your beam will fail at a very, very early load, very early load, because simply the governing here is the tension. And because concrete is not really as great in tension as in compression, so it fails at a very early load. You can see the load is very, very little, 24 kilonewton, okay? How about if I add some reinforcement? Let me show you. For example, if this beam was not plain concrete, if this beam has some reinforcement here, I'm going to show you. Let's say, let's add some rebar on the bottom. So what happened here, once it will start the same. So when you have increased the load from 0 all the way to 24, guess what? Your entire beam is uncracked. Your section is working in both compression and in tension. But as soon as the force is 24, then this is where you can see the first crack in tension. If this beam has no reinforcement, congratulations, the beam will fall to the ground. How about if we have some rebar, so even your beam cracks at the bottom because the concrete stress at the bottom is equal to the modulus of rupture. However, because you have some rebar, so the rebar will take over and the beam will still hold and carry more load. And maybe we can do this exercise when you learn in my class today. How can this number, so if we have a plain concrete, it can take 24, okay? Now, what happens if I put some rebar? Is going to be 26 or is going to be maybe way, way more than 24? The answer is way more than 24, and you will learn today and next class about how do we estimate the number if we place some rebar. Okay, again, any questions so far? Okay, if no question, I guess. Any questions so far? No question. Then let's move today's class. So today's class, I would say we are starting today the real business. The real business. Yes, in the last 4 weeks, we've done introduction. We looked at loads. We looked at structural or statical analysis. I'm not saying those are not important, but I know some of you maybe by now question, where is the design? When can I do the design? When can I find my rebar? You will start seeing those things in action today and through the whole week. Okay, so I have a presentation, and today, trust me, it's going to be very detrimental for our relationship, or maybe your relationship to my course. So whether you will be in love with this course today, I mean, not today. As I said, you always have to be patient. But if things make sense for you today, I would say this will make you more connected to my class. Okay. Now, what will be covered today? I'm going to talk again about notations and symbols I'm going to use in my design. Number 2, we will look at the concrete beam behavior after cracking. Remember, what you've seen so far is before cracking. Before the beam cracks at the bottom, then you know what happened. As soon as we exceed the cracking moment, then the beam will behave differently. Okay, and then we'll talk about something called the beam failure modes. You will learn about this today. And then we talk about design versus check. And then we give you, as usual, numerical example, so you guys can understand those difficult equations. And then we end up with balanced beams. I don't think that I'm gonna cover the entire material today. However, we will see. Something also I wanna mention a few things before I start. Number 1, on this part, there is an assignment. And always, I'd like to give you the assignment earlier than it should be. I'm not going to wait until I finish the material and give you the assignment. The reason is, if you want to have your assignment early, you start even before I finish the material, you can do that. So you have more time than the promised of 1 week. Okay. So far, when you check the assignment on the D2L, you will see it is due to the next Wednesday, which means it is about 10 days from today. This deadline is not fixed. It depends on my progress of my material. Whenever I finish the entire material required for the assignment, then it will be 1 week. So if I'm able to finish by Wednesday, then it's going to stay the same. If not, then the deadline will be pushed to Friday of next week. So okay, again, there is no rush. You will study the material, and you will have 1 full week to solve it. I understand totally that you're stressed and you have so many assignments, and that's why I always give you, as I promised initially, 1 full week. Some of you guys asked me last class about the midterm exam. So the midterm exam, we will agree, me and you, together on the midterm exam on Thursday. On Thursday. So we have 3 classes still. Then this Thursday, we will agree on what is going to be the date for the midterm exam. It is going to be whether the last class on the 7th week or the first class on the 8th week. But again, it depends on our progress. There are so many things has to happen before I, give you my midterm exam. There are some assignments need to be marked, need to give it to you, or there should be a model answer for all those assignments in your hand. I'm gonna decide on that. Not yet decided. Okay. Now. Okay, guys. Now, quickly, you've seen this slide before. That's not new, but it's good time to kind of remind you of all the notations on this slide, because you kind of need to memorize those notations. So, for example, the beam width, I'm going to always call it as letter B. Okay. Now, for the depth of the beam, there are 2 depths. One is called overall depth, or depth, called H, which is measured from the top of the slab to the extreme fibers and tension at the bottom of the beam. There is another depth called D, and you can see I put it in red. So guys, when I color something on my slide, this means you have to pay attention. So the D we refer to as effective depth, which is measured from the same point from the top of the slab, but not to the bottom fibers. It is to the centroid, or the center of the gravity of the main reinforcement. When I say main reinforcement, I said this last time, and I'll say it one more time. There are 3 different colors for the rebar in my cross section. There are some in pink, there are some in cyan, and some others in green. When I say main reinforcement, I'm referring to those 3 bars in pink. This is the centroid. And I think the last class, we had 3 different examples on how to find the centroid of a group of rebar, whether symmetric or unsymmetric, whether it's 1 layer or 2 layers. You have that on the slide. Please, also something I want to say it. I want to stop here for a minute. Guys, listen. When I give material, the material is for the. I spend a lot of time to produce for you this material. Hope that the quality of the material is to your expectation. Okay, but please, I'm not here to study the material for you. You have some role in the process. Okay, and I know that some of you maybe think it's easier to ask Tahir about the question and save my time. I don't have to watch the video. I don't have to read the slides, but I can simply send him a message on MS Teams and he will confirm. Please be considerate. Okay. I'm not going, otherwise there's no point of recording the videos. Otherwise there's no point of creating material if you're going to ask me every single question. Do your part, read the material before you even ask me. If the question is not in the slide or not in the video, then this is the time you ask me. Okay. Now, the next element, which very, very important, something called rho, which is kind of a Greek letter. It's called the reinforcement ratio, which is the area of the steel divided by area of concrete. And again, explicitly, it is going to be area of steel of the main reinforcement divided by the width of the beam divided by the effective depth of the beam. So H is not included. It is D. And as always expressed as percentage. We say it's 1%, 2%, 3%, 0.5%. We always express the reinforcement ratio in percentage. Also, the last class we went through and explained for you the spacing, and also the concrete cover. Okay. And so let's move on to our next slide. And I probably will see the slide so many times in my design course. Okay, now when you look at this beam one more time, it's a beam, but this time it is not a plain concrete. This beam is not like the one that I had it a few minutes ago. So those are different, okay? Because this one, again, if I delete this bar here, this one was plain concrete, no reinforcement, but this one it has some reinforcement. Guys, listen. When I apply uniform load, as you see on my slide, when I apply uniform load on a simply supported beam, what happens is this will cause a bending moment or cause your beam to bend. And the bending moment diagram is not new. You've seen this last year. You've seen it one more time in my class this year. It is going to be a parabola. And the parabola, whether you draw the parabola on top of your beam or at the bottom like I do in my screen, on my screen, both of them are right, and the value is WL squared over 8. Hopefully you remember that. Whether you draw your bending moment on the top or on the bottom, really what's important for me is to know where is the tension and where is the compression. So if you look at the cross section of the beam, which is shown next to here, this is the cross section of your beam. Okay, most important for me is to understand where is the compression stresses and where are the tensile stresses. If your load is a gravity load, so what happens is you guys can feel it, whether you draw your bending moment on the bottom or on the top, then the bottom fibers will be in tension and the top fibers will be in compression. And as I said before, the way I draw the bending moment, to be honest, it matches and it's best fit in this class. Because if you simply draw the bending moment the way I do it on my screen, right away you know that you have to put your reinforcement at the bottom side of your beam. Okay, and look at the cross section. Yes, we do. We have 3 bars here in red because this is the tension side of your beam. Now, what I'm trying to say here is when we add some forces, some loads, and this load will cause some bending moment, and the bending moment exceeds the M sub CR. Now, let me remind you, what is M sub CR? It is in the previous slide. So the M sub CR is cracking moment, It's the moment that will cause the bottom fibers of your beam. The stress arrives at F sub R, which is modulus over. So if the bending moment exceeds the M sub CR, then because the beam has some reinforcement, so the beam will still hold up and carry more load. If your beam has no reinforcement, what happens is your beam is going to crack and immediately will fall to the ground. Okay. Now, what happens? Look, you can see here is my situation right now. Don't focus so much, please, about the different forces. So this one here, the loads, they were uniform loads, and in this picture here, we have 2-point loads, P and P. Doesn't matter. It doesn't matter. The thing is, whether it's uniform load or point load, both of them, they cause bending moment. Once the bending moment exceeds the M sub CR, then your beam will crack. You can see I'm going to point out the cracks. So the cracks are presented here. The cracks are there. And why the beam still holds? Because it has rebar. And the rebar will simply take care of the tensile stresses on behalf of the concrete. Now let's look at one instant where the beam is about to collapse. Okay. Now what happened is, look at the stress. So please focus in this area. I'm going to draw a box around this area here. So guys, this box here, what you see inside the box is a stress diagram. And we agree that everything above the neutral axis is in compression and everything below the neutral axis is in tension. So you can see there are one thing in above the neutral axis, which is concrete. However, at the bottom of my neutral axis, there are two things. One is the rebar in red here. So those are the rebar. And also there are some concrete in tension. And the thing is, which I'm going to say it for only one time, only one time, only one time. Even concrete is not really good in tension. However, still take a little bit of tension, a little bit, very little, like 3 MPa. And that's why you can see there is a little portion of the stress diagram which is here. So what's this part here? Concrete is in tension. The resistance is not zero. However, it's very, very little. And the rest is carried by the rebar. But please note the following, that this part here will be neglected in my analysis. So I will neglect all the concrete effect in tension as if it doesn't exist. So really the rebar will take 100% of the tensile forces under the neutral axis. Okay, so I said it one time, only one time, but you will never see this part in my next derivation. Why? Because I said that the tensile resistance of the concrete in tension will be neglected. We only use concrete in compression, and then the rebar will be in tension. Okay, here we go. So I'm going to cross this part out. Okay, so here we go. I'll do this one, and this part here, this little part here, will be neglected. Okay, for a future derivation. Now, what happened, guys, is you can see here. I'm going to talk right now about one moment when the entire beam fails. Okay, so as I said before, if your beam is a plain concrete without any reinforcement, then we know when exactly the beam will fail, which is when the bottom fibers of the beam, the stress is equal to F sub R, so that's cracking, and then the beam will collapse. Now, when we add some rebar, then we know, because we have some rebar, the beam will not collapse. However, it will hold more loads. Now, I'm talking about, again, going even beyond and keep adding loads until my reinforced concrete beam is going to collapse. So what you see on my screen in the box is the stress diagram of my beam, of a reinforced beam before the beam collapses. Okay, now, I know things are getting dry, but hopefully you will get better insight in a few minutes. So guys, this is what happens before your beam collapses. A few things, probably we already said one. So number one is concrete tensile stress is neglected in calculations. Okay, so that's our assumptions. Okay, so the concrete tensile stress is neglected. Only rebar and concrete in compression. Number two, the strain in the concrete before the failure, which is, we talked about it last class, I guess. It is epsilon. It is not E, it's epsilon, which is a strain, and then sub C maximum. C is for concrete, and maximum, it means maximum before concrete fails. I'm referring to this number here, or this name here. The way it is epsilon C maximum. And as I said before, this number is complicated. However, the code gives us this number. In our design, we're going to use this number as 3.5 per thousand, 0.0035. Okay. Now, it's good for now. So let me move on to the next slide. And I'm going to come back to this number 5 later on. Okay. Guys, this is not new. You've seen this before. This is the relationship between the strain and the stress. Strain and stress. On the right side is for rebar, and on the left side is for concrete. Do you guys remember that? I need some noise, please, because looks is very quiet. Do you remember that this curve here is the relationship between the stress and the strain for concrete, and this is the stress and strain for rebar? Okay.
Yes.
Thank you. Now, we also learned in my class that we're not going to use the bolded one. The bolded one is really the full F field. However, I said before that we will apply something called resistance factor. And resistance factor are reduction factor. It means we're going to assume because of the variability of the material, and we are going to assume less than F field. Those numbers are something called phi sub S and phi sub C. Okay, so you guys remember the numbers are 0.85, so 85% of F yield. So we take the entire curve and then multiply it times 85%. Same here, we take the entire curve and multiply by 65% because of the variability of the material, because we are not 100% sure that my rebar will always be 400. I'm not sure that always my concrete will be 25 MPa. So we take kind of factor of safety by applying resistance factor or reduction factor for resistance. 65% for concrete and 85% for the steel. Also, guys, I said before in my class that you will never, ever, ever see F field by itself. So this number, you will never see it by itself, never. However, what you will see always, you will see this number, a reduced value for F field. Same thing, you will never see FC dash by itself. However, you always see in my derivation a modified or reduced FC dash by a factor of 65%. Okay. Okay, next is. Now, I want to probably mention something here. The relationship between the stress and strain is different in concrete and steel. For the steel, the relationship is linear. Look at this. So from 0 to the F field, the relationship is a line relationship. However, for concrete, it's a parabolic shape. And this will create a little bit of difficulty, which we will solve in the next slide. Okay, watch this, please. So I'm going to zoom in here. I'll zoom in here and I will repeat what I said a minute ago. So guys, listen to me, please. I said we are going to neglect the resistance of concrete in tension. Do you see that? You don't see this part anymore. It has been removed. So only concrete in compression, which is here. So this concrete in compression. And this is rebar in tension. Okay. Now you can see, even though my beam is going to under bending moment the planes is going to rotate linearly. However, the relationship between the stress and strain is not linear for concrete, and that's why look at this curve here. So this curve is your parabola. This curve is the parabola. Okay. So it is parabolic shape here, and this, guys, this creates a problem. Okay, and I will show you how. I need to ask you questions and I need somebody to answer me, please. Okay, let me ask you, if we agree that from this discussion here that the relationship between concrete and between stress and strain in concrete is not a line relationship, it is parabolic shape. Everybody tell me please, where is the centroid of this area? Anybody, did you learn in any math courses? Is it easy? Is it difficult? Just say one word. Is it easy to find the centroid of the parabolic shape?
No.
Okay, thank you. So yeah, the centroid of the parabolic shape is not really easy. It needs something called the integration, and integration is not an easy process, and it's just we're not going to do that. Okay, so again, one more time, this curve I'm pointing to right now is parabolic shape. Parabolic shape are, yes, we can find their area, yes, we can find their centroid. However, it needs a complicated mathematical treatment. Now, let me ask you, if I do one magic, I'm magic in minutes, but let's say I do some magic and I'm able to convert the left to the right. I'm asking you, do we have any mathematical advantage if we simply are able to replace my parabolic shape by a rectangular shape? So where is the rectangular shape? It's here. So this, guys, this here is a rectangular shape. Now, let me ask you the question one more time. For a rectangular shape, can we find the area and the centroid easy, or it's difficult?
It's easy.
Very, very easy. And that's exactly the advantage of this transformation. Okay. So really, when you break a beam, This is the reality. The left is the real picture. That's exactly what's going to happen when you break a beam. The stress will be parabolic, and however, even it's reality, but we cannot derive a simple equation based on this. I'm going to show you how easy, if we're able to do the magic and convert and transform this parabolic shape into equivalent rectangular shape, while we know it's not going to happen. So this is not going to happen in reality. So this one is not going to happen in reality. This is only to make my life easy in the derivation of the math. Are you guys following? So the reality is the left one. However, very difficult to deal with, because you will see I need to know what's the area. I need to know where is the center of the gravity. However, if I'm able to transform the parabolic shape into an equivalent, look at the name, equivalent rectangular block, then you will see how easy my math is going to be. But knowing the following, that this is going to happen in reality, while this is only for the purpose of my derivation and calculation. Now, how do we do the magic? How do we convert our parabolic shape into equivalent rectangular shape? Here we go. We need only two parameters. One is called alpha 1, and the other one is called beta 1. So let me point out those numbers. So here we go. We have here an alpha 1, okay? And the beta 1, I'm going to show it to you here. Unfortunately, this snapshot from the book doesn't show it, but I will show it for you guys. But here we go. The beta is simply the relationship between the A and C. Anyway, so please hold on. I'm going to explain for you what is beta 1, what's alpha 1. Beta 1 and alpha 1, those are transformation factors. When we use them, simply they will transform my parabola, which is very hard to deal with, into equivalent rectangular block, which is easy to deal with mathematically. Now, let me show you something before I explain in more details. Guys, look at this, please. You guys know that this point here, we have zero stress, no tension, no compression. And what do we call this line? I mentioned the name last class. The abbreviation is here, NA. But what's NA? Anybody knows what's NA?
Neutral axis.
Thank you. So the neutral axis is where you have no stress, no strain. NA, neutral axis. And you can see my curve comes to zero here. Look at this. So my curve comes to zero here. However, when we convert our parabola into equivalent compression block, then just mathematically, the relationship between the base, you can see the bases here. I'm going to probably put dimension line to guys so you can see. The base of my equivalent compression block is over there, okay? So this dimension is the base. So what is the relationship between the location of the neutral axis as marked by C? You guys know this is the C. And what's C? It is the location of the neutral axis from the top fibers. And what is A? Simply the A is simply the base of your equivalent rectangular block. So here is beta 1. Beta 1 is simply, the equation is here. So A is equal to beta 1C. A is equal to beta 1C. Now, let's look at the stress. So guys, we said before that I will never ever say FC dash by itself. You can see the maximum stress will never, in my assumption, will never be FC dash. However, I'm going to always use a reduced version of FC dash, which is phi C multiplied by FC dash. Now, what happened is, in order for you to convert and transform the parabola into equivalent rectangular block, guess what? There is a new something here new. And all you have to do is, you just have to multiply your phi C FC dash or F prime C by a factor called alpha 1. Alpha 1. Okay, now, before I give you the details of how do we estimate alpha 1 and beta 1, let me ask you this question. Just think of now that we're able to do the transformation. Mathematically, is my life easy to find the area of the block or to find where is the centroid? Let's see. If this is a rectangle, where is the centroid?
H/2.
It is not H/2 because maybe my dimension line is covering the H, but look at this, please, okay? This dimension is not H. H is the total thickness or total depth of your beam, okay? But this line here is A, which is the depth of the equivalent compression block. So I think you got it, because simply if this rectangle, it means the centroid is here at this level. I'm going to point out where is my centroid. So my centroid is here. Where is the location? Simply you take A, you divide it by 2, then you know where is the centroid. Now, what is the area? The area of this equivalent rectangle is simply like any rectangle, base times height, base times height. So the area of this guy is equal to A multiplied by alpha 1 phi C FC dash. Guys, hopefully you see, I know so far we still need to do more mathematical work, but at this point of time, all I'm asking you is to appreciate when we transform the parabola into an equivalent rectangular shape, then we get some mathematical advantage, because simply we know right away, very simple, that the centroid is in the middle of A, and also the area is simply the length times the width. Are you following? I need to hear some noise.
Yes.
Anybody else who can say yes, please? Or no?
Yes.
We're following.
Okay, thank you. Anyway, again, one more time for whoever is shy or maybe doesn't follow, the reason why we go from the actual one, which we know is actual, which is parabolic, to a mathematical replacement, is this one here will be so easy when we start derive some equations. The thing is, we're converting a parabola into equivalent rectangular block, and it's not very difficult. We have to simply take the C, which is the base of the parabola, which is location of the neutral axis, to multiply it by something called the beta 1, a modification factor, and we take the stress, which is phi C multiplied by F prime C, we multiply that by alpha 1, so we now done it, we have done it, now we have transformed our parabola, which is difficult, into a simple equivalent rectangular block. Now it's time to know what's alpha 1 and what's beta 1. So the code on page 63, equation 10.1, equation 3.5 and 3.6. Guys, here are the two equations that the code give us to find alpha 1 and beta 1. Alpha 1 and beta 1. Let me zoom in so you guys can see. So very simple equation. The alpha 1 is equal to 85% minus 0.0015 FC dash, and it has to be more or equal than 0.67, okay? Beta 1 is 0.97 minus 0.0025 F prime C, and it has to be more or equal 0.67. Okay, which means it's become very simple. All I have to do is, if I know the FC dash, I can use those equations, and then I can find alpha 1 and beta 1. Now I'm gonna even make your life way easier. Now guys, anybody remember last class when I kind of discussed what is the normal range of FC dash? Are we making concrete like 80 and 100 MPa? Are we making concrete 5 MPa? What do you think? Anybody can remind me what is the normal range of FC dash that you will see in my class?
20 to 30.
Anyone else? Thank you. Anyone else?
40.
30 to 40.
30 to 40. Anybody else?
20 to 40.
Say it again, sorry.
20 to 40.
Mahdi is right. It is 20 to 40, not 30 to 40 or 20 to 30. In this class, you will see concrete always between 20 to 40. Now, guys, let's try to, and please, I want you guys to do it on your own. So if you have a calculator, please go ahead and find for me the alpha 1 and beta 1 when FC dash is equal to 20. Let's do that. Not very difficult, very simple. Look at this. So I'm saying here, replace the F prime C by 20 and find for me alpha 1 and beta 1. It's going to take a few seconds, huh?
0.92.
That is going beta 1. Right?
Yeah, that's beta 1.
How about alpha 1?
0.82.
Thank you, sir. Thank you, sir. Can somebody do it for 40, which is the other extreme?
For alpha 1, it's 0.79.
Thank you, sir.
0.87 for beta.
Okay. Here is the good news for you. So I kind of make something which will make our life easy. Okay. So when the concrete compressive strength varies between 20 or 25 to 40 MPa, and that's what we are going to use in this class, guess what? The alpha 1 and beta 1 roughly, approximately, is going to be 0.8 and 0.9. Okay. And please, so in this class, I will not ask you to use those equations. Okay, although they are available, if you want to use them in situation where FC dash is beyond the 20 to 40, then do. And remember, it cannot be alpha 1 cannot be less than 67%, and beta 1 is the same deal. So guys, agree with me, please. In this class, anytime from this point until the end of the classes, anytime we want to find or we want a value for alpha 1, it is 0.8. Anytime we want to find a value for beta 1, it's 0.9. Okay. So again, let's try to show you this one more time on the diagram. So this means the A is 90% of your C because the relationship is through beta 1. So A is 90% of your C. How about here? Okay. Look at this, please. So guys, you know that phi C is equal to 65%. And if my concrete is 25 MPa, so this number is 65% of 25 MPa. Guess what? If we want to do the transformation, all we have to do is multiply the same number times 0.8. And here we go. We're able to find this. One thing I want to mention, alpha 1 and beta 1, they have no units. Do you see that? Alpha 1 and beta 1, they have no units. Do you see that? Because this is MPa, and if we even multiply by alpha 1, it's going to stay as MPa. And then A and C, those are distance. If we multiply C by beta 1, we get A. So which means beta 1 also, it has no units. Okay. And by the way, this discussion, again, is purely for our derivation, because using equivalent compression block seems to be way easier than dealing with a parabolic shape. Okay. And that's what you see, by the way, here. If you go back, that's statement number 5. Statement number 5. Okay. Now, here is the final look. Here is the final look. Now, in my class, since I showed you the actual one, but from this point on going forward, you will never see parabolic stress diagram. What you will always see is this guy here. You will see equivalent compression block with the dimension is equal to A is equal to beta 1C. So which is this dimension here, which is the base of the equivalent compression block, and with a stress value equal to alpha 1 phi C FC dash, and the compressive force in concrete is in the middle because that's the centroid, which is A over 2. At the bottom here, we have our tension in the rebar. Okay. Now, one thing also to remind you when it comes to the stress, so what you see here is the stress diagram. When it comes to the strain, as I said, in the concrete will be epsilon C maximum. At concrete will be epsilon sub S. Okay. A 3D picture even will do it even better. What you see here is a 3D picture of what's going on in your beam. At the bottom, there are my rebar. Here we go. So those are my rebar. What they do is they simply take the tension force, which is here. So this will be the tension force. Okay. At the top, concrete is fantastic in compression. We've seen it will act in reality as parabolic shape. We remove this one, convert it into equivalent. This guy here is called equivalent rectangular block. Dimensions are the depth is equal to A, and then the width is equal to the width of your beam, B, and then the stress is equal to alpha 1 multiplied by phi C multiplied by F prime C. Okay? Probably, guys, need some dimension. I'm going to show it to you one more time. So the width is here. It's from this point to this point, and this is the width of the beam. It's called B. And then finally, the stress is from here, from this point to this point here. So this number is equal to alpha 1 phi C F prime C. Are you following?
Yes.
Okay. Now, guys, I know this is kind of very dry, so I'll give you a break, okay? And please be patient. Be patient, okay? I know when things are in just a mathematical presentation, like equations and unknowns, is very difficult, but please be patient until you see things in numbers. It will be super easy. Thank you, and I'll see you guys in 8 minutes. I'll see you guys sharp at 2. Thanks.